Welcome, everybody. Welcome. This is the first Seattle area group tinyML talk. So thank you very much for coming in tonight. We have a very special guest, Chris Hoge from OctoML, who's the developer relations person there. And let me see. I lost my mouse again. Great. Oh, I got it. Cool. Nope, I'm good, Chris. Great. Welcome, and let's get started. Thanks, everyone, and to our sponsors. I'll go into more of this later, but these are the tinyML Talk sponsors. Some of these should be very familiar to you. Some of these may be less familiar, but if you're in tinyML, you should at least be aware of them. The next tinyML talk is going to be Tuesday, March 2nd. It's going to be Eben Upton, the founder of the Raspberry Pi Foundation, and he'll be talking about inference with Raspberry Pi Pico and RP 2040. That should be a really good one. I'm very excited for it. He's one of the founders. And the Raspberry Pi Pico, if you haven't gotten your hands on one, try. It's a lot of fun, and it's like $4. And there's already a lot of support and things that work with it. I think ArduCam. Anyway, check it out. Also, check out the documentation for that Pico because there's already a lot up. If you are interested in presenting, contact talks@tinyml.org. Webcast start time is 8 a.m. Pacific time. The local committee in Seattle right now is me. If you are interested in joining the committee or helping me out or want to present, feel free to reach out to me. It's carl@tinyml.org. We can also send me a message while you're here and we can chat about stuff. We will have to do more of these, so I'm always going to be looking for speakers. And plus, when things change and we can meet in person, which will be really nice, hopefully we will have in-person meetups. So we'll have to figure out how to do that as well. Announcement, the tinyML Summit is next month. It's March 22nd to 26th. Sign up for it now. It is free, which is great. I've been I was just there last year. Really good talk. tinyML community is obviously getting much, much larger all the time. New companies, new hardware, new research. There's going to be a lot of really good sessions, a lot of good research papers. So definitely check it out. The schedule should be up soon, I believe, but register now. It's a really good conference. As I was saying, tinyML is growing fast. 2019 was basically when it started with the first summit, had roughly 160 people with 90 companies, no kind of community whatsoever. By last year, the 2020 summit, it was 400 plus people at the event, 172 companies, and a larger growing online community. At this point, we're expecting 3,000 people more and 300 plus companies at the summit this year, with a huge online community. If one thing has happened in the last year is the online community has grown even better. There's tons of these meetups. We do talks all the time. It's a good community. So welcome, and thank you for being part of it as starting the local Seattle version. Summit sponsors are going to be all of these companies, which you definitely know most of them. If you're interested in sponsorship, contact sponsorships@tinyml.org. Reminders, slides and videos will be posted tomorrow. So both Chris Hoge's slides that he'll be talking about, those will go up on the forums. And then this video recording will go up on the YouTube channel, which is youtube.com/tinyml. Please use the Q&A window for your questions. One, so it's easier for me and Chris to answer them. And two, if we don't get an answer, we always try to get those answered and post them up on the forums. And that's a great way to record them. With all of that being said, I'd really like to introduce Chris Hoge. Chris has more than 10 years of experience in helping build open source communities, including strategic program management for the OpenStack Foundation and as a SIG co-founder in the Kubernetes community. He has a background in applied mathematics and lives in the Pacific Northwest. With that, Chris, take it away. Thank you so much.
Fantastic. Thanks, Carl. And I want to say good day to everybody. Thanks for coming to this talk. As mentioned, I'm Chris Hoge, and I'm a developer advocate for Apache TVM. And I have a background in mathematics and applied mathematics and computation. But I've really been working in open source and open source infrastructure projects for a while. And so being able to work as a developer advocate for Apache TVM, which is a machine learning compiler framework, is something that's really special to me, because not only does it give me an opportunity to go back to my roots of applied computation, which I love, but to also come at it in a new direction that I haven't really explored very deeply. OctoML is one of the sponsors of Apache TVM, but there are a number of different members in the community, including ARM, who have a lot of active developers who are contributing to TVM. And so in this talk, we're going to talk about a little bit about an introduction to Apache TVM and TVMC. And what I would like us to walk away from this presentation is for you to have an understanding of, at a high level, what Apache TVM is doing, how it works, but then also practically how to get started with it using the TVM application front end. And so we're going to do this in a number of ways. We're going to start off by talking about why you should use TVM. And then we're going to go into some details about how TVM works. Now, these are going to be some higher level details. We'll dig in a little bit to how things are working under the hood, but we're not going to get too deep in that. In the how does TVM work section, I'm really just interested in giving you a high level painting of what it means for TVM to be a compiler framework and how it can benefit you. And then we're going to go into the details of how you can get and install TVM. And then finally, how do you use TVMC? Okay, so let's start off with why should you use TVM? Oh, and while I'm giving the talk, feel free to ask any questions. Carl is going to be watching the Q&A. And if you feel like there's a question about something I'm talking about right now, please feel free to ask the question. We can stop, we can talk about it. Okay, so let's start with just setting the stage for this. We're talking about a simple image classification example. Say that you have some sort of classifier that is going to take images. It's gonna look at those images, do some sort of evaluation, and then spit out an answer of what I think it is. And so there are a couple of phases that when you are trying to solve this problem. The first phase of this is training the classifier, also known as training. But we're not really terribly concerned with this. Like, we can assume that there are lots of classifiers out there, that there's been a lot of research done, there's a lot of existing models, there's a lot of literature on how you build your own models, and frameworks and platforms for being able to do this. But when we go to the second phase, deploying the classifier, this is what we're interested in talking about. And we have to answer a number of questions when we go to the deployment phase of our models. For example, what hardware are we going to run it on? Is it going to be running on a CPU, some sort of GPU and cloud, some sort of very low power embedded device? As you're making these decisions, especially as you start moving to the lower power embedded devices, you start making trade-offs between how fast you want the model to be and how accurate you want it to be. Whether you're doing that through, you want to quantize your model, or you want to change it from floating point to integer computations. And then finally, you need to decide what actually you're going to be running it in. Is it going to be on a Windows platform, on a Mac, a Linux, some sort of embedded operating system like Zephyr? What languages are you going to use? Is it going to be Python, C++, C, Rust, or some other language? And when you think about this, it actually winds up being a fairly large challenge for when you want to deploy a model. If you look across the top of this matrix, you have all of these different devices. And then down the left side, you have all of these different frameworks and platforms that you can develop your models in. And let's say that you've developed your model in TensorFlow Lite and you want to deploy it to an ARM CPU. Hey, well, you're in luck, because TensorFlow Lite has a great compiler that is able to target the ARM CPU, and you can get your model off of TF Lite and onto your ARM chip. But let's say that you were deploying your model in Caffe 2. Well, then you're in trouble, because Caffe 2 doesn't have a backend that can target this hardware in the ways that you might want to be able to do it. And this is a problem that is only getting worse within the machine learning community. the number of platforms is increasing within the ecosystem, but we're also seeing an explosion in the number of devices and how those devices are configured, whether they be general computing devices or devices that are specifically targeted towards tensor computations, or devices that are meant to be embedded and try to have as much throughput for machine learning as they can with as low power as they can. And this is where TVM comes into place. So TVM is an open source optimization framework for machine learning. It can ingest models from a number of different frameworks, including PyTorch, TensorFlow, ONNX, and MXNet. And it can target a number of different devices, including x86, ARM, NVIDIA GPUs, AMD GPUs, MIPS, and RISC-V. It also supports a number of different operating systems, including Linux, Macs, iOS, Android, Zephyr OS, Windows, and WebGPU. And with TVM sitting between your platform, between your development platform and your deployment platform, you're able to not just compile models to run on those platforms, but also be able to optimize them. So TVM is open source. It's an official Apache Software Foundation project. Right now we have over 500 contributors who are contributing to the project. Over 6,000 stars, 2,000 forks, and it continues to be under active development. It's community owned, and so even though I work for OctoML, and a lot of the people who are at OctoML are working on this project, we also have contributions from a number of different organizations within industry. And indeed, one of the reasons we put it into the Apache Foundation was to guarantee that it was a community-owned project and was developed and operated in a way that meets the needs of the community as they evolve. We have active discussion forums, and so if you go to discuss.tvm.apache.org, we have a full set of forums there. There are posts to it every day. You can ask questions, you can request features, and it's a really great community of people who are always happy to help both new and experienced users. And finally, we have regular meetups and conferences. And so we have a monthly meetup every Thursday. The third Thursday of every month at 9 a.m. Pacific time, as well as an annual conference. And we're right now, we just had our last conference in December of 2020. All of the videos are online, and we're planning out for the next year, and we'll be announcing sometime in the next few months the dates of the new conference for 2021. Okay, so what sort of problems is TVM addressing? Well, we've kind of covered these a little bit before, but we're looking at TVM addresses the problems of portability. How do you take a model and apply it to what might be a limited set of hardware options that you have? Efficiency, when you need a model to run as effectively as possible on a particular platform. And what this means to run effectively on a platform can change quite a bit depending upon the architecture of that platform, as well as software support. Let's say that you have new and unique hardware, and a software stack just doesn't exist for you yet. TVM provides you a lot of tooling to be able to compile your machine models down using existing open source tools to target those platforms. Okay, so let's get into the next section of the talk, which is how does TVM work? Now, I mentioned before that I want to take a very high level view of how TVM is structured, because it's a platform. It's not a program by itself, but rather it's a larger platform that allows for extension, that allows for changing, that allows for making it target the things that you need. And as such, it can be very complex and it can be very daunting. And so what I'm hoping to do in this next session is, by giving you a high level overview, I want you to understand some of the terms that we're talking about when we talk about TVM, what the layers are and what's happening at each layer, so that as you begin to use TVM, and TVMC is a great way to start working with TVM, because it kind of introduces you to these concepts while providing a nice interface around it. You'll be able to understand that when you need something more powerful from TVM, where to look for it. Okay, so what we have here is an architecture diagram of TVM, where at the very bottom, we have the lowest level of the layers, all the way up at the very top where we have the higher level abstractions. And we're going to walk through a number of these and talk about what they mean. So TVM provides a runtime, and the runtime is the foundation of the TVM stack. It's able to load and run compiled TVM artifacts. Now, the runtime has a number of different implementations, including a C and a C++ implementation, with the idea that you're able to take a TVM model and a very small runtime and deploy that to wherever you need it to be able to run. TVM also support, and because the runtime is written in C, and there's also a runtime written in C++, it's also highly portable for different devices. Sitting on top of the runtime is an intermediate representation layer. And this is what we call the low-level compiled intermediate representation. This is the thing that gets translated into the runtime. And it has all of the unified data structures and interfaces for all of the function invariants. And so, you know, as a model is compiled and as it's optimized, it's going to be lowered into the intermediate representation before it's then compiled and lowered down into the runtime. Sitting directly above that is the TIR module, which is also the tensor intermediate representation. It also includes a number of low-level language invariants, and it represents functions that can be transformed into equivalent functions by multiple passes. And so it's a higher level language. It's meant for you to be able to express tensor operations, but do them in a way that is highly mutable so that you can modify how the computation happens while still preserving the fundamental computation, what that computation is doing. And so if you're doing a matrix multiplication, if you're doing a convolution, it retains the inputs and outputs of that, but allows you to compose it in different ways. We also have a target module. Now, the target module is what allows us to target different sorts of architectures. And it allows the IR code to be transformed into a runtime object. Also allows TVM to target different architectures. And so, for example, a target might be LLVM. And when you set LLVM as a target, you wind up opening up a number of different options for targeting different architectures. And so you can use the target LLVM and then tell it that you're going to be running on an ARM CPU, and all of the machinery for that to happen will take place behind the scenes. Targets are extensible, and so if you have a new platform that you want to be able to compile optimized models for, you can we call it bringing your own compiler, and by fulfilling a number of different abstract APIs, you are by providing representations for those, you should be able to target new hardware. Okay, so now we're going to go a little bit deeper and talk about one of the oldest but most important components of TVM, which allows a lot of this machinery to work. And this is the Tensor Expression module. Also, it's commonly referred to as TE. And the TE module is a domain-specific functional language that allows for the templated expression of tensor computations, which can then be transformed in TIR passes using schedule operators. And this is such a fundamental and important concept of TVM that we're actually going to dig into this just a little bit more so that you can see what's happening with it and why it's such a powerful abstraction. And we're gonna frame this within the context of a very common operation, matrix multiplication. And so if you're familiar with matrix multiplication, it's you take two matrices that conform to a particular, whose inner dimensions conform to a particular size. There is there's a vector multiplication or a vector reduction across every row and across every column of the matrices to produce a new matrix which conforms to the outer dimensions of both of the matrices. And the naive implementation of this is to represent it as a triply nested loop. Now, matrix multiplication is one of the fundamental computation problems. And if you consider Blass's Matmul operation, that was created in the 70s to help support the space program. And there's been a ton of research for how it is optimized for different architectures. And so on the right here, you see that there is an optimized approach, which is just a snippet taken from thousands of lines of code. And when you go from the naive implementation to the optimized implementation, you can have an implementation that is 10 to 100 times faster. Okay, so let's take a look at what this looks like inside of TE and TIR. At the very top of the screen here, we actually define matrix multiplication within the Tensor Expression language. And so this is being programmed within the Python interface. And so what you have is you have the reduction axis that the multiplication is being performed upon. You have two matrices, a matrix A and a matrix B, which we're calling them placeholders, and we're giving them dimensions. And then we have a matrix C, which is an output of computation from that. And so what we see here is the TE compute has a lambda function, which is the an operation, a TE sum operation, which is the multiplication of A and B across the axis K. With this in place, we can create a default schedule. Now, one thing that's important to remember about the tensor expression is everything that you see in these variables, K, A, B, and C, those are abstractions of what the computation looks like. You can talk about with the size of the tensor that is going into it, the size of the tensor that is coming out, and the sort of computation that you want to do. But we're not actually reifying the computation. It's just a high level, purely functional expression of the computation. One of the nice things about purely functional expressions is that they lend themselves very well to transformation, so that transformation that maintains variance. And so in this case, our invariants that we want to maintain are the input size, the output size, and the computation that's happening inside of it. From here, we can create we can tell TVM to create a default schedule. And the schedule that it produces looks a lot like our naive implementation of matrix multiplication. But because TE is a functional language, we can start performing operations on that operation, which maintain those invariants, but allow us to take advantage of the structure of our architecture, ways to improve matrix multiplication. And so, for example, we can compute tilings, which tries to pull blocks of the matrix into smaller chunks of memory so that we can take advantage of caching. And so here we apply a tiling. We call this in TE we call this a tile schedule. We can give it a block size. In this case, it's 32, but we could pick any block size that we wanted. We might have picked 32 because it allows the size of the blocks to fit nicely into the cache for our particular system. And then we can do some things where we reorder the operations so that we can move data access closer to one another. So once again, we can take advantage of the architecture. All of this is done abstractly. But then when we call the when we lower the schedule into code, then what we have below is the code that is emitted is 6 nested loops. And so by applying these abstractions to the tensor expression language, we're able to kind of build out these optimizations and do it in a way that might be very error prone if a human is coding it manually. But TVM is very good at being able to express this automatically based off of the original schedule. And we can go further. Like a lot of modern CPUs include vector operations where you can perform where you can chunk data that is sent to the chip and perform addition and multiplication, vectorized and parallelized at the these are through SIMD instructions or through AVX instructions, and so once again, And this is why we did this split before, where we were splitting the data up, because a lot of SIMD instruction sets will vectorize across 4 floating point values. So you can split according to those 4 values. You can do some reordering to get those values to line up with one another, and then you can do a vectorization on that. Again, adding another layer of optimization. And when you look at the output of applying these operations, you can go from creating a basic schedule, which is just your 3-level nested loop, to adding a number of different lines which reorder the data, which vectorize it, and do it all in a way that preserve the computational invariance to produce code that is more likely to be optimized for your target platform. And with about 13 lines of code, we can increase performance by about 200 times. So the tiling and loop permutations lead to better cache hit rates. Array packing turns non-continuous access patterns into continuous patterns. Vectorizations take advantage of special hardware instructions. And thread level parallelization makes use of all of the cores. But hopefully one of the things that you're asking yourself is, well, that still seems like a lot of work, and it seems like I have to have a lot of knowledge about the underlying architecture to be able to pull this off successfully. And so that brings us to the higher level features of TVM and the value that TVM brings for optimizing computations. The first of these is the layer called Topi. Now, Topi stands for the Tensor Operator Inventory. And it's a collection of predefined TE templates that cover a range of common operations for a different range of platforms. And so we can talk about Topi templates for targeting CPUs for matrix multiplications and convolutions, or for softmax operations. These can also be targeted towards GPU. They can be targeted towards embedded devices. They can be targeted towards quantization. And I've mentioned the word templates, but templates are kind of a way to, if we go back a few slides and we look at this slide here where we have this block size of 32. Well, templates within Topi are a way for us to give us a knob that are able, where we can tune that block size so that we can try different values and see, and see if we can get better results from trying different values within the templated values. So it looks like we had a question come up.
Yes, you did. Timothy asked, do you have a detailed report or paper for this research?
Yes, we do. We do, absolutely. And there are actually a number of different papers. There are 4 of them that kind of that have been published throughout the years, and it's almost like reading an epic. I don't have the links for this talk directly, but I can try to dig them up, and we can get them into the slides so that you should be able to reference them later once we reach out to everyone.
Yeah, one more question from Mahmoud. When we are talking about memory optimization, or where can we figure out all the resource usages? Thanks.
Yeah. So with memory optimizations, these are, we're right now the community is working on a profiler to be able to evaluate both the time and the memory impacts of what TVM is doing. So it can be a little bit opaque. Like, one of the main cost functions that TVM is using is just how quickly something runs, and so it's just looking at the speed on a device. I don't have a deep knowledge of how to write a cost function which targets memory usage, if the discuss forum is actually a really excellent place. If you have a particular application you're looking at, the members of the discuss forum would be able to point you in the right direction of where you needed to look. Okay, so then now we're moving on to the like the higher level functions of TVM and the really powerful tools that have been built upon these lower layers. And these are AutoTVM and the AutoScheduler. And these are both components that automate the search for an optimized schedule. This includes tuning records, creating tuning records, so conducting experiments on top of the CPU to see how well tuning parameters are working, different cost models, and so it tries to infer a cost model for a CPU to make predictions about where it needs to search in the space to improve performance, feature extraction, and search policies. And so it's actually worthwhile to dig in a little bit to see actually what AutoTVM is doing. And so when we talked about TE, you remember that we were talking about expressions. We were talking about schedule search spaces. We were talking about templates that had tunable knobs for that we could adjust parameters to try, to just try different programs and see which would run fastest on the CPU. And once you've created this framework where you have a number of parameters that you can adjust, and a cost function, which in this case is an execution time, you can put an object in between there, which takes those measurements and tries to search that space for an optimal solution. And so we have an objective function, which is searching for the arguments that produce the minimum function value over the search space. So you have an expression, you feed it into AutoTVM, which creates some sort of it'll modify the schedule in a way that is invariant. It'll generate code that you can run on a platform, and then you get a cost, which is the execution time. And with those pieces in hand, you can then build a feedback loop where you can start searching the space and also build statistical cost models so that you can guide the search through that space towards what is hopefully an optimal solution. And in this way, you can look at each operator within some sort of computation and find out what the optimal configuration for your platform is. And the nice thing about this too is where previously when we were talking about using tensor expression languages or writing, or making bespoke algorithms, a lot of times that required the programmer to have a deep knowledge of what was happening on their target architecture. In this instance, you don't need to have as much knowledge of the architecture because you can allow TVM to search for different configurations that will perform optimally. Okay, finally, well, not finally, so two more components that we want to look at. The next is relay, which is an even higher level functional intermediate representation that is used to represent full models. And it can support different dialects of optimizations, including quantization, memory optimization, and dynamic virtual machines. But the idea behind relay is that models don't operate, the different layers of a model don't operate on their own. And if you look at a typical model, you can see that there are all sorts of different things that are happening in each layer. And so you have, here you have, convolution, 2D, followed by a batch norm, followed by a ReLU. And every time you perform one of these operations, you have multiple memory accesses where you're grabbing the input data, you're grabbing the parameters for that computation, you're doing the computation, and you're writing it to an output buffer, which is then fed into the next buffer. And you can ask yourself, is this many memory accesses really necessary? And so relay gives you the opportunity to fuse multiple operators into single operators to minimize memory access. And so this is just one of the optimizations that relay can perform on a computational graph. And so if you have relay, and if you had to rely on an operator library, every time you added a new operator that you wanted to have fused, you would have to add a new implementation. But by using the lower level code generation techniques that TVM offers, you can start generating fused kernels on demand. And so you can think of the optimizations that are happening at different levels, where relay is applying higher level optimizations, and then TIR and TE are applying lower level optimizations.
1 second, Chris. Another question from Timothy. What platforms are supported? So I have a follow-up question. Timothy, do you mean hardware or software? Because it's basically all of them, right, Chris?
Yeah. I mean, it's very extensive. Like pretty much any hardware platform you can think of. If TVM doesn't support it, support can be made available for it. And so one example we like to talk about is Microsoft was working on these very small embedded devices. And that literally had no SDK for it at all. And a researcher at the University of Washington was able to take TVM and the C runtime and target installing machine learning models onto that device before it was practically running anything else. But out of the box, it supports all variants of Linux. It supports embedded devices, including small devices like ARM CPUs, even smaller devices like embedded devices, and so it actually has a very large ecosystem. It also has a number of different API interfaces, and so if you wanted to work in Python, if you wanted to work in C++, Rust, Go, these are all platforms that TVM has API support for. Okay, so if we look at like TVM was able to, the TVM definition and schedule implementation for depthwise convolution 2D is less than 700 lines long, which is far less than the 13,000 lines that tinyML uses for, not tinyML, TF Lite uses for its implementation. And not only this, but it can cover a multitude of different kernel sizes, not just 3x3, and as well as many different data type implementations, not just uint8. And then finally, TVM has a number of different front ends where you can pull in models from different frameworks. And so this could be Onyx, this could be TensorFlow, this could be PyTorch, and it's with the goal being that if you had a new front end that you needed to support, you could start writing new operator translators to pull all of those in. Okay, so since this is tinyML, it's actually worthwhile looking at the results that you can get with TVM on a system like Raspberry Pi. And so on this graph here, we have TF Lite versus TVM with what we call an auto tuner running, and versus TVM with what we call an auto scheduler running. And these are just different implementations of algorithms to search optimization space. In auto tuner, you need to provide your own templates to be able to optimize against. And with the auto scheduler, it'll draw from more of a from a bank of different pre-existing bank of templates and be able to schedule on its own. And you can see significant performance improvement across a number of different common models, including MobileNet v3, Coco SSD Mob, PoseNet Mobile, and YOLO v3 Tiny. In a number of instances, as much as 3 times performance increase. Okay, so now we get to how do we install TVM? So we've been working pretty hard on making installation of TVM very easy, and this is through tlcpack.ai. TLCpack is independent of TVM and of the Apache Software Foundation. And this is largely because we also want to be able to ship TVM with some vendor specific libraries. But we want to make sure that we are staying within, coloring within the lines of how Apache Software Foundation wants us to distribute software. And so TLCpack is run by a number of different volunteers who are working on bringing Conda and pip installations. You can also install from source. It's fairly easy. But if you go to tlcpack.ai, you can find your platform, your preferred package manager, and do an installation there. Now, we're still working on building out the support. And so if you're running on Linux, right now, Conda is the only thing that's supported. We're working on improving that. My goal is to have pip nightly supported. I also recommend that you grab the nightlies. The 0.7 release, which is the stable release, is fairly old. It actually looks like they've bumped it up to the 0.8 dev release, and so in recognition of that. But you're going to get the most features out of TVMC in particular if you're using the nightly release. Okay. So then we're going to get to the practical portion of this talk, which is how do you use TVM? And so we've talked about all of these features. We've talked about them at a very high level, but how can you start seeing the benefits and seeing if TVM is right for you? And TVMC is a great way to get started with that. Okay, and for this demonstration, we're going to use the ONNX representation of ResNet 50 v20. And so we're going to start with that model. And for those of you who aren't familiar with it, ResNet 50, it's an image classifier. And so it takes an input image that is 224 by 224 with 3-bit depth. And then it classifies it according to, a number of different possible classifications. Like, in this case, ResNet would look at this picture and say that, well, I think it's a tabby cat, but it could also be a tiger cat. And then, and then the values drop off pretty quickly, and it thinks that, well, maybe there's a very slight chance that it could be a radiator. But yeah, it did a pretty good job of identifying that this was a tabby cat. So for this demo roadmap, we're going to download the ResNet 50 v20 model in ONNX format. We're going to download a test image. We're going to compile the ONNX model to TVM's internal graph representation, relay. And then we're going to run it, and we're going to see what the results are like. And then we're going to create a tuning record of the model with TVM. We're going to create an optimized model with TVM to compare the timings. And then time permitting, I'm just going to go through really quickly, like how you can do some cross compilation and do some remote tuning and running of models on different hardware. Because we are moving pretty quickly. So we're going to we have about 15 minutes to get through to get through the demonstration. So this code is available. I have it available as a make file. I'll be updating it as we finish this talk to incorporate some new changes that I have into it. But for downloading the ONNX ResNet 50 v2 model, it's just a command to go grab the model. We're going to grab some of the information about the model and some of the labels. Once that's done, we're going to go grab this image of a kitten. You could replace it with any image that you wanted, as well as perform some processing of it. And so, one thing that you'll have to remember is that TVMC is going to want to take data in as a NumPy matrix, and so whatever data you're bringing in, you're going to want to convert that to the appropriate size in NumPy to be able to feed it into the model. Similarly, when the data comes out, you're going to want to have to post-process it to do some sort of evaluation on it. And these files are also included that we need to do this. And then we're going to compile and benchmark the model. So let's switch over to here. And so what we want to do is we're just going to run make tvm.txt. And so this is going to perform all of those first steps, right? It's downloading the kitten, it's downloading the ONNX model, it's downloading the ResNet model. And so we're doing a live demo here. And then we're running a TVM compile operation where we're compiling the model to the TVM to the relay format. We're specifying that we're using LLVM and a specific CPU as our target, so that TVM knows which optimizations it can perform on that model. And then it takes a little bit of time to compile it here. And then finally we run the model and we produce some benchmarks. And so if we print out the output of that tvm.txt file, we get a runtime. It's about 112 milliseconds, which is okay, not great. But we're seeing that we're making the same predictions that we expected before. And so in some sense, we've confirmed that, okay, like we're making the right predictions. We have a baseline that we're working from. Now on the next thing that we're going to do is we want to make the TVM auto tune file. And so we're going to do an auto tuning, and then we're going to recompile the model and see what comes out of that. so so essentially we're calling TVMC tune. And so, and I'll actually, after this, I'll actually run TVMC to show the options that are available for it. So previously we did a TVMC compile where we ingested the model, we produced an output model. Then we did a TVMC run where we took the model that we generated, we ran data through it. You can do batch operations on this. You can read in multiple data. You can run it multiple times. And so TVMC can serve as your inference front end if you want it to be. Now, tuning takes a long time. So instead of running all of the tuning, instead, it is outputting. So tuning is just doing that search. It's searching, it's trying different configurations, and then it's saving the output from that in a file that can be used later for tuning. So make sure we don't have any threads running. Whoops. But I've run this job before, and I have, if we look right here, I have a cached set of auto tuner records, and then so we can do the same thing. But let me show you what the what this looks like for. So we have the unoptimized results. We do our TVMC tune, running our target, and then it's going to run through all of the computational layers in the graph that it knows about, and then it's going to just perform a number of operations and try to find the optimal solution. And you can see that it'll output what the result of the current test is on the CPU, but also what the fastest configuration that it found for each of those operations was, and how long did it take to do each of these. Then we can take the output of that, and we're gonna generate a new model, which is going to be optimized, that we can then benchmark. And so we're going to use the cached version of this. Whoops. Based off of the auto tuner records that I generated before. So this is another thing that you want to keep in mind too. If you're just looking at optimizing to run a model a few times, it takes a long time and it takes a lot of computational effort to do it. The time to optimize your model is when you're ready to put it into production, and you know that you're going to be running a lot of different inferences through it. And that's where you're going to see the savings. The savings are going to aggregate over time as you're running the number of models. So we finish the compilation, we do the run. And let's compare the two results. So in this case, we almost got a 2 times performance increase from the baseline of TVM versus the optimized model. Okay, so are there any questions that we can answer about that right now? And it's like kind of when we've seen what is TVMC doing?
There are 2 questions. One was, when do you think pip support for Linux will happen? Any idea if you had a guess?
I want it within weeks.
Yesterday.
I want it now. We just need someone to do it. And I've been trying to write new documentation for TVM to make it easier to come into TVM and start working with it. So a tutorial on how to run TVMC, a tutorial on how to interact with TVM through Python. And when I finish with that, if that task is still outstanding, it'll probably be the next thing that I do. And so it's very high up on my stack of my stack of things that I want to accomplish.
Cool. Or Timothy, who asked the question, if he gets there first, maybe he can do it.
Yes, yeah. If you get there first, it would be fantastic. Yeah. It's open source. It's at the tlcpack.ai repository rather than the TVM repository. But yeah, we have we're producing Mac Nightly builds, and so it shouldn't be that hard to be able to. I think the thing that is the hard part about kind of like doing this is we want it to be able to run on as many Linux platforms as possible.
Yeah.
And so we're trying to build an all Linux package rather than, building from like, an
Just
Ubuntu
Ubuntu or just Debian.
Um, okay.
Timothy also asks, if I want to use a Raspberry Pi, does it require any additional hardware? Do you have a tutorial for it? I have RPi Model 3 with 1 GB RAM. Is that sufficient? So what are you running? What Raspberry Pi are you running?
So I don't have a Raspberry Pi in hand yet. I tried to order one and get it here before this talk so that I would be able to do those demonstrations. I just ordered an RPi 4 with 8 gigabytes of memory, but because we're using LLVM as a cross compiler for this, which we're actually going to get to in the next section of the talk as we're kind of winding down to the end, you can actually target anything that you want. And you do need to know which platform you're targeting because it'll change your LLVM target string. But this kind of segues nicely into, like, let's say that we want to do remote execution with TVMC using remote procedure calls. Well, TVM has a framework that allows you to do that. It uses an RPC tracker, which you can run on basically any platform that you want. And the tracker is going to have 2 key pieces of information associated with it. There's going to be a host name and a port number. And then on all of your target devices, you can run clients on those that, when you give it the host name and port, as well as a key for what type of platform it is, it will communicate with the RPC tracker, say, hey, I'm alive, I'm available for work. And this can be a heterogeneous pool. And so you can assign different keys to different platforms, which you then have a TVM client. In this case, it can be TVMC, which you can do cross compilation on that client, request a job be run on the RPC tracker, and then the cross compiled code will be sent to the target along with the input data. The job will be run, and then the data will be sent back to the client. And so how is this done with TVMC? Well, in this case, you're going to do a TVMC compile. You're going to specify a target. And so in this case, if you're going for a Raspberry Pi, you're going to say that it's an ARM CPU and a 64-bit Linux architecture. You're going to specify a cross compiler. And so, like Ubuntu, you can just do a yum install for a GCC cross compiler, and then you specify an output file. And so this is using the TVMC compile. Then when you get into the TVMC run, you add a few new options. In this case, you give it the RPC tracker with the tracker. So this is the IP address, the port. You specify the key. So recall before we said that all of the clients need a key to be able to identify what type of platform they are. And then instead of giving it the model that's been compiled for your platform, you give it the cross-compiled model, and it'll send the model over. It'll run it, send the results back to you. And this is really nice because if you have a bunch of Raspberry Pis, you can actually do parallel tuning. And so TVMC is also, it's RPC tracker aware. And so if you have, like a Pi cluster of the, it says 3, 5, or 10 Raspberry Pis in it, you can set up the client on all of those, point them to the tracker, and then you can do a distributed tuning of your model before you deploy it. And so it supports both running and tuning. Okay, so that brings us to the end of our talk. If you want to know more, we have a discussion forum at discuss.tvm.apache.org, as well as docs, which are there to help you get started with TVM. I'm working on a major refactorization right now, and so if you're familiar with kind of like a Kubernetes the hard way, I'm working on, maybe it's more of a TVM the easy way, but a way that really guides you through the entire stack of TVM in a way that helps you understand it, so that no matter where you are in your machine learning journey, you should be able to either use the high level features and just compile models and run them, or dig down a little bit deeper and start writing your own kernels and optimizing them for your own platforms. This code is available at my GitHub at hodgepodge/TVM demo. The code for TVM is available at GitHub/Apache/TVM. We have monthly community meetings. We just had one this morning at 9 a.m. Pacific time, the third Thursday of every month. You can find Apache TVM on Twitter. And we also have another talk, which is an excellent companion to this that we gave last month at tinyML Tokyo, which is an introduction to micro TVM. Now, micro TVM allows you to target embedded devices. And so it'll handle things like converting from floating points to integer types, has a super tiny runtime so that you can deploy the models onto it, you know, in the very constrained spaces that we have. It's aware of the constrained memory and hardware resources that you often have in these devices. And so it covers some of the same ground here, but it also covers another entirely different aspect of TVM, which might be of interest to you. So I highly recommend that you go and you check it out. If you want to reach out to me, again, my name is Chris Hoge. I'm the developer advocate for Apache TVM. And so it's my job to help the community be successful with TVM. And you can reach out to me through my email, choge@octoml.ai, or at hodgepodge on Twitter. And thanks. With the time that we have left, I am happy to answer any questions. We also have a tinyML Talks feedback that it would be fantastic if you could vote on that. And I'll let Carl take us out.
Thanks again to all the sponsors, the tinyML Talks sponsors specifically. That is ARM, Edge Impulse, Keto, SynSense, DeepLight, Maxim Integrated, and Reality AI. ARM, the software and hardware foundation for tinyML. We do a lot in terms of tinyML solutions. We contribute a lot through TensorFlow Lite Micro, so that's going to be the way to do it until micro TVM is like super easy to use, and we're also contributing there. DeepLight, we use AI to make other AI faster, smaller, and more power efficient. Become a beta user, by the way, at bit.ly/testdeeplight. They do have a beta going on right now. tinyML for all developers. This is Edge Impulse. If you're just getting started, I would recommend it. It's fun. They have a free account. I built a dog snore classifier because I had no other data sitting around that was readily available, and it was a great 2-day project. Maxim Integrated enabling edge intelligence. They do health sensors. They do a lot of work around hardware acceleration, and then they focus on AI on the edge. Keto AutoML for embedded AI, automated machine learning platform that builds tinyML solutions for edge using sensor data. Reality AI is for building products. And SynSense builds ultra-low power sub-milliwatt sensing and inference hardware for embedded, mobile, and edge devices. We design systems for real-time, always-on smart sensing for audio, vision, IMUs, biosignals, and more. Again, the next talk is going to be Tuesday, March 2nd. It's Eben Upton, who's one of the founders from the Raspberry Pi Foundation. He's definitely one of them. So that would be a good one. Check it out.